Доброго дня, шановні друзі. Сьогодні вчергове Київський національний університет спільно з Малою академією наук та Європейською молодіжною академією наук приймає проєкт лекції майбутнього. Це проєкт спрямований на те, щоб в Україну привести знаменитих науковців, діячів. Вже протягом останніх 1,5 роки ми запросили в Україну 15 різних видатних людей з усього світу. Серед них 4 Нобелівські лауреати. Сьогодні черговий візит Нобелівського лауреата. На цей раз у нас в гостях лауреат Нобелівської премії з фізики 2015 року з Японії, професор Кадзіта Такаакі, який виграв премію 2015 року спільно з Артуром Макдональдом за відкриття нейтринних осциляцій. На сьогоднішній день професор є директором Інституту космічного випромінювання Університету Токіо та директором та керівником дослідницької групи Super-Kamiokande. Сьогодні професор прочитає лекцію протягом 1 години. Це буде наукова публічна лекція, після чого ми запропонуємо півгодини сесії питань-відповідей для наукової сесії питань-відповідей, для наукових запитань. І після ми вже нова традиція, яка започаткована 1,5 року тому, на всіх наших лекціях після наукової частини ми пропонуємо ще спілкування неформальне, де ви можете, і професор це підтримує, де ви можете задавати питання, не пов'язані з наукою, це мотивація, успіх і так далі. Тому сьогодні у нас такі 2 години можливостей зустрічі з великою людиною, лауреатом Нобелівської премії з фізики, професором Кадзіта Такаакі. Для вступного слова я хочу передати слово президенту Національного центру Мала академія наук України, приймаючої організації, яка запросила професора в Україну.
Приємно сьогодні приймати фізики, тому якраз вам буде дуже цікаво. Всі молоді люди зараз знаходяться у пошуку розуміння, що таке Всесвіт, який це Всесвіт. І ви знаєте, питання, які хвилюють вже 2 століття, це питання темної матерії, темної енергії. Це такі фундаментальні питання не лише фізики, а й людського існування, світогляду. І якраз професор Такаакі Кадзіта отримав Нобелівську премію за осциляції нейтрино. Тобто ви знаєте, що нейтрино – це елементарна частинка, нейтральна, її неможливо було зафіксувати. Вважалося, що вона не має маси, питання це дискутувалося. Але якраз відкриття професора, пов'язане з осциляціями нейтрино, показало, що ці частинки можуть мати масу. І це, звичайно, величезний вибух призвело у фізичній, у науковій, взагалі в інтелектуальній спільноті 21 століття. Я думаю, що ви зможете з перших уст задати питання професору, що таке темна матерія. Може він нам пояснить і розкаже. Тому що був, звичайно, Стівен Хокінг, але теоретично він не мав можливості довести експериментально існування чорних дір і так далі. Ви це добре знаєте, його видатні лекції. І, мабуть, я думаю, професора можна буде спитати, чому Стівен Хокінг не отримав Нобелівської премії. Він дуже хотів отримати Нобелівську премію. І якби тепер, коли вже підтверджено існування чорних дір, темної матерії, можливо б, якби він ще трошки прожив, він би став лауреатом Нобелівської премії. Я ще раз вітаю пана професора у нас в гостях і запрошую його до лекції.
Well, thank you very much, and good morning. This morning, I want to talk about neutrino oscillations and small neutrino mass. Well, okay, so on the screen, you see a photo of something, and in fact, this is the Super-Kamiokande experiment. Well, with this detector, we have been studying neutrinos, and here today, I'm going to talk about our studies of neutrinos using these underground detectors. Okay, so this is the outline of this talk. First, well, I guess some of you do not know about neutrinos, therefore, I have a brief introduction on neutrinos. Then, I want to discuss our activities in Kamioka, that is the location of our experiment. Then I want to move on to the discovery of neutrino oscillations. That means that neutrinos have small mass. Then I want to talk about the status of neutrino oscillations and the importance of neutrino mass. And before finishing this talk, I want to mention about the future prospect. Actually, in fact, this morning, I realized that this part could be too technical, therefore I may skip some slides, but I just simply want to say that neutrino studies are likely to be still very important in the future. So this is the outline. Now let's begin. What are neutrinos? Well, neutrinos are fundamental particles like electrons and quarks. Well, but still you have no idea. So let me say that neutrinos are something like electrons without electric charge. In fact, this is really, in my opinion, very good answer to what are neutrinos. And because of the no electric charge, neutrinos can easily pass through even the Earth. But neutrinos can sometimes interact with matter. Therefore, we are able to study neutrinos by observing very rare interactions of neutrinos. Now, in addition, I want to say that neutrinos, like the other particles, have three types, namely electron neutrinos, muon neutrinos, and tau neutrinos. And finally, I want to mention that in the very successful standard model of particle physics, neutrinos are assumed to have no mass. However, of course, physicists have been asking, neutrinos really have no mass. And indeed, we found that neutrinos have very small mass. Okay, so this is the very brief introduction to neutrinos. Now, I want to talk about our activity, scientific activity. Well, the whole history began almost 40 years ago. In the late 70s, grand unified theories of elementary particles predicted that protons should decay with the lifetime of about 10 to 30 years. of course, 10 to 30 years is a very long lifetime. Therefore, the proton lifetime does not affect our daily life. However, because of the scientific importance, people began proton decay experiments in the early 80s. And one of them was the Kamiokande experiment. And, well, you can see the sketch of the Kamiokande experiment. It was an underground experiment. Well, in deep underground, we constructed a very large water tank. It had about 60 meters in diameter and 60 meters in height, and it contained 3,000 tons of pure water. And inside this tank, we installed multiplier tubes or photodetectors in order to detect photons that are emitted inside the tank. Well, if a proton decays, well, if one of the proton in water decays, then typically we expect 2 to 3 charged particles are emitted. And then, if this charged particle propagates in the water, these particles emit photons called Cherenkov photons or Cherenkov light. And these Cherenkov photons are detected by photodetectors. And by observing these photons, we may get information on the lifetime of proton or evidence for the proton decay. That was the idea. By the way, maybe you do not know the location of the experiment. Well, the experiment was located there in the rather mountain area of Japan. In fact, the photo of the site looked like this. Well, here, if you carefully look at the photo, you realize several buildings. Actually, they are the facilities for the mining activity. And we installed a Kamiokande detector inside in one of these mountains. Well, of course, we have to construct the Kamiokande detector. And therefore, the on-site construction, for the on-site construction, we came to the site, and this photo was taken in the spring of 1983, where we constructed the Kamiokande experiment. Here, at the center, you see Professor Koshiba, who was my thesis advisor, and also he was the Nobel laureate in physics in 2002 for the detection of supernova neutrinos using this Kamiokande detector. Anyway, this photo was taken when he came to the construction site. By the way, behind Professor Koshiba, there are 4 young students, and they were the students of Professor Koshiba, and these 4 students really worked in underground for several months to construct the Kamiokande detector. And one of them was actually me. So, and this photo was taken in the morning before going into the mine. And well, after that, we took a mine train to go inside. Well, when the Kamiokande experiment was constructed, the mine was really an active mine. So every morning, we took this train together with the miners. The train left the entrance at 7:10 in the morning, and we worked deep underground until late in the afternoon. And the actual construction of the detector was like this. Well, of course, first we had to excavate the underground cavity, then the steel tank was constructed. After that, physicists, we came into the construction site and we installed the photodetectors onto the detector wall, well, tank wall. But there was an issue. As I said, the height of the tank was about 16 meters. Therefore, it was an issue how to how to install the photodetectors onto the detector wall. Well, we had a lot of discussion on how to install the photodetectors, and finally, we decided to use rubber boats to install the photodetectors. Well, we installed the photodetectors at some height on the boat. Then if we finished one row, then we raised the water level by 1 meter. Then we installed another layer of photodetectors. Obviously, working condition was not so great. Our floor was kind of shaking, but still we were able to finish the installation of the photodetectors, and we began the experiment in July 1983. And of course, we wanted to observe proton decays. And before starting the experiment, we hoped that we could observe proton decays maybe every week or maybe every month. Unfortunately, proton lifetime was longer than expected. So we were unable to observe proton decays. Instead, we observed neutrino interactions. Actually, these neutrino interactions are the most serious background for the proton decay search. Therefore, we have to observe these neutrino interactions, and we have to carefully analyze these neutrino interactions in order to separate the proton decay signal and the neutrino background. And these neutrinos are created by the cosmic ray interactions in the atmosphere. Cosmic ray particles interact with the air nucleus, then pions are produced, and these pions are, of course, unstable, therefore they decay to muon, but muons are also unstable, therefore they decay to electrons. And during this decay chain, neutrinos are produced. And of course, most of these neutrinos pass through the Earth, but some of them interact in the Kamiokande detector. And if they interact, they are the most serious background to the proton decay search. Anyway, even after 3 years, we still wanted to search for proton decays. But of course, after 3 years, we have many background events. Therefore, we wanted to improve the analysis of the proton decay search. And for this, we developed a new software to improve the proton decay analysis. Well, this improvement, improved software, well, actually, there are several new software to improve the protonic analysis, but one of them was a software to identify the particle type for a Cherenkov ring. Namely, we wanted to know if a Cherenkov ring like that is produced by an electron or by a muon. In fact, this is one of the event patterns we observed. This Cherenkov ring was actually created by a muon. That was muon-neutrino interaction. Anyway, we wanted to know if a ring was created by an electron track or a muon track. And of course, as usual, if we have a new software, we have to test this new software extensively. Usually, new software contains many bugs. Therefore, we have to remove all the bugs in the software. So we did a series of tests. And at the final stage of the test, a neutrino type was studied for the atom-sec neutrino events so far observed in Kamiokande. Then, unexpectedly, it was found that the number of muon-neutrino events was much fewer than expected. Well, I said we have to test the new software, and this was a test. The result was unexpected. This means it is most likely that there is some problem in the new software. So we started various studies to find mistakes in the new software. In fact, we did really an extensive studies to find a mistake. And in fact, we tried to find a mistake for almost 1 year, but we didn't find any serious mistake in the software package. Therefore, finally, after 1 year, we concluded that muon-neutrino deficit cannot be due to any major problem in the data analysis nor the simulation. So we decided to report what we observed. And in fact, we published our first data on this analysis. The histogram I show in this slide is the main part of the paper we published in 1988. In this paper, we reported the number of muon-neutrino events observed. That was 85. Then compared with the simulation, that was about 144. Clearly, data showed a significant deficit. And in addition, we did the same counting for electron-neutrino events. And for electron-neutrino events, the data and the simulation agreed reasonably well. Okay, that's all we reported in this paper. Well, we really simply reported what we observed, but actually the world community reacted rather negatively. People discussed what was the problem with the Kamiokande experiment or something like that. Anyway, we had more than 1 year of studies on this problem. Therefore, we had high confidence that we didn't have any serious mistake. So we thought that there must be something interesting suggested by this data. Of course, I said something interesting. Actually, we didn't know what was happening, but we thought that there must be something new suggested by this data. So I thought this data would be very important. Therefore, well, I decided to concentrate on the studies of neutrinos. In fact, before that, I was interested in the search for proton decays, but I switched my study from proton decay searches to neutrino studies. Well, that was the 1988. Unfortunately, there was no supporting data. And finally, in 91 and 92, another large water Cherenkov detector, IMB experiment, also reported the deficit of muon neutrino event. And this photo is the inside of the IMB experiment in the United States. So finally, with the result from this experiment, people begin to be a little bit more serious about what was discovered by the Kamiokande experiment. That was the muon neutrino deficit. Anyway, with the muon neutrino deficit only, it was really unable to conclude the cause of the deficit. However, from the beginning of these deficit, we thought that maybe the cause was due to neutrino oscillations. Well, I'm afraid I cannot go into detail of the mechanism of the neutrino oscillations, but let me tell you simply the result from the neutrino oscillation hypothesis. If neutrinos have mass, neutrinos change their type from one type to the other. For example, here in this graph, if a muon neutrino is created at location 0, and if they start propagating in the vacuum, then at some point, the probability that muon neutrino to remain muon neutrinos goes down. But if they propagate further, the probability come back to unity. If they propagate further, the probability go down, go up, go down. This way, the probability that muon neutrino to remain muon neutrino oscillate. Then, when muon neutrino, when the probability that muon neutrino to remain muon neutrino go down, at that point, tau neutrino is appearing. So this is the neutrino oscillations, and if this is happening, then the muon neutrino deficit observed in Kamiokande and IMB can be explained. By the way, here I assume the students, therefore I decided to use this graph. But if I speak to the general audience, I show this kind of graph. A muon neutrino is created, then if they propagate, then muon neutrino change the type to tau neutrinos. Then if they propagate further, then the type of neutrino come back to muon neutrinos, then tau neutrinos, and so on. Okay, so from the beginning, we thought that the deficit could be due to neutrino oscillations. However, of course, many people can propose many other ideas. Therefore, we really wanted to have evidence, clear data that shows the deficit is due to neutrino oscillations. And for this, we thought this way. Well, atmospheric neutrinos are created everywhere in the atmosphere of the Earth. Therefore, some of the neutrinos are created in the upper atmosphere, maybe 10 to 20 kilometers above us. Then these neutrinos only travel 10 to 20 kilometers before interacting in the detector. 10 to 20 kilometers could be a short distance. Therefore, these neutrinos may have no time to change their type. On the other hand, neutrinos are also created in the other side of the Earth. These neutrinos must propagate in the Earth before interacting in the Kamiokande detector. Therefore, these neutrinos have to travel long distance, typically 10,000 kilometers. 10,000 kilometers is a long distance. Therefore, these neutrinos may have enough time to oscillate. So, if this idea is right, then we should observe the up versus down asymmetry of the atmospheric muon neutrinos. And if this is observed, then we thought this could be the evidence for muon neutrino oscillations. Unfortunately, the 3,000-ton Kamiokande detector was too small to observe this effect. We needed a much bigger detector. That was the Super-Kamiokande detector. Now, I want to move on to the studies of neutrino oscillations in Super-Kamiokande. Super-Kamiokande is a much larger version of the original Kamiokande experiment. It has a diameter of about 40 meters and height also about 40 meters. And it contains 50,000 tons of pure water. And it is also located deep underground. By the way, this is an international collaboration. We have about 160 to 170 collaborators from 10 countries. And in fact, this experiment began as an international collaboration. This photo was taken in 1992 when we had the initial discussion on the collaboration in Super-Kamiokande between Japan and the United States. Well, as I said, in the 80s, there were two underground large water Cherenkov detectors. One was Kamiokande in Japan, another was the IMB experiment in the United States. And with this meeting, these two experiments decided to work together in Super-Kamiokande. And in fact, the meeting went well. As you can see, several beer bottles. So the international collaboration began in 1992. And in fact, this was, the Super-Kamiokande was constructed as a 5-year project period. The construction, excavation began in 1991, and we were supposed to begin the experiment in April 96. The first was the excavation of the big underground cavity, and then the construction of the water tank. Then, in 95, physicist Super-Kamiokande collaboration came to underground to install the photodetectors onto the detector wall. So this photo was taken in the spring of 95 when we constructed, or when we installed photo detectors onto the Super-Kamiokande tank. Of course, Super-Kamiokande is a very big detector. Therefore, the installation of the photodetectors onto the detector wall is non-trivial. We needed many people. So every day, these many people worked for the construction of the Super-Kamiokande detector. And actually, in fact, I want to say that about 70 to 80% of these people are physicists, collaborator of the Super-Kamiokande experiment. So in 95, we physicists worked in underground for almost 1 year to construct a Super-Kamiokande detector. Anyway, the construction went well, and in January 96, we started filling pure water into the Super-Kamiokande tank. And this photo was taken from the top of the Super-Kamiokande tank, viewing inside. And you can see the water level. At that time, the water was almost half of the height. And experiment, in fact, began in April 96. And since this was the second generation water Cherenkov detector, therefore people knew how to operate the detector. And in fact, from the beginning, we were able to observe many neutrino interactions. These two photos, not photos. These two view graphs shows the typical events observed in Super-Kamiokande. The left one is a typical electron-neutrino interaction event, and the right one is the typical muon-neutrino interaction event. Here you can see rings, and well, colored rings, and in fact the colors show the timing. Red is first, and blue is late. And also the size of the circles show the photon intensity observed by each photomultiplier tubes or photodetector. So every day we observe about 10 neutrino interactions per day. Actually, 10 neutrino interactions per day is, for us, was a very high event rate. In the Kamiokande era, we observed only 1 to 2 neutrino events per week. So 10 events per day was really a high event rate experiment for us. Anyway, from the beginning of the experiment, we knew that neutrinos could be very interesting. Therefore, we concentrated on the studies of neutrinos in Super-Kamiokande. And because of the concentration of our studies on neutrinos, we were able to report our first result in 2 years. we reported our result at the Neutrino Conference 98. And this is one of the slides we presented at the conference more than 20 years ago. And, well, first of all, you notice that the technology was very different. Well, I think these young people have no idea what are shown. Actually, 20 years ago, we copied our data, our histogram, onto a transparent plastic film. Then we wrote down several comments onto these sheets, film. And then we projected these transparent sheets onto the screen. This was the way we presented our result in physics conference 20 years ago. Anyway, the reason I show you this slide is due to the importance of the data shown here. In particular, the lower one is very important. The lower one is for muon-neutrino interactions, and the horizontal axis shows the arrival direction. And cosine theta 1 means neutrinos coming from above. And minus 1 means neutrinos coming from the other side of the Earth. And of course, cosine theta 0 means neutrinos coming from horizon. And clearly, oh, by the way, black dots with error bars show the data, and the squares show the simulation prediction. And clearly, for downgoing neutrinos, the data and the simulation agreed quite well. But for the neutrinos coming from the other side of the Earth, data show almost a factor of 2 deficit compared with the prediction. And this factor of 2 deficit can be very well explained if we assume neutrino oscillations, namely muon neutrinos created in the other side of the Earth. While they propagate inside the Earth, they change their type. Muon neutrino, tau neutrino, muon neutrino, tau neutrino, and so on. And therefore, when they arrived at the Super-Kamiokande detector, the probability that muon neutrino to remain muon neutrino is half. Okay, so this way, we presented our data, and physicists were convinced that muon neutrinos do oscillate to tau neutrinos. Okay, so that was the announcement of the discovery of neutrino oscillations. Well, of course, as physicists, we simply announced our discovery at the conference for physicists, but I think we were very fortunate. President Clinton gave a talk at MIT's 1998 commencement, and in this speech, he mentioned about our result. Of course, the whole speech is long, therefore, I only show you the part that was related to our experiment. He said, just yesterday in Japan, physicists announced a discovery that tiny neutrinos have mass. Now, that may not mean much to most Americans, but it may change our most fundamental theories from the nature of the smallest subatomic particles to how the universe itself works. and indeed how it expands. And of course, as the US president, he mentioned that US contribution to the Super-Kamiokande experiment. Then he come back. The larger issue is that these kinds of findings have implications that are not limited to the laboratory. They affect the whole of society, not only our economy, but our very view of life, our understanding of our relations with others, and our place in time. So, well, this was the President Clinton's speech. And I think we were really honored to hear this kind of speech by the US president on the next day of our announcement. Okay, well, that was 20 years ago. I wonder what will happen if the discovery were 20 years later. Anyway, now, okay, so that was 20 years ago. Now, I want to briefly discuss the progress after the discovery of oscillations. Now, after the discovery of muon neutrino to tau neutrino oscillations, several more experiments have been studying more details of the oscillations. This is the list of the experiments studying muon neutrino to tau neutrino oscillations. Some of these experiments studies atmospheric neutrinos, or some of these experiments generate neutrino beam using an accelerator. Then neutrinos are detected after, say, several hundred kilometers or more distances. And in fact, these experiments study neutrino oscillations in detail. Now, I want to switch to other neutrino oscillation discovery. Well, here I show you the photo of the first solar neutrino experiment at Homestake gold mine in United States. This pioneering Homestake solar neutrino experiment observed solar neutrinos for the first time about 50 years ago. And because of this discovery, Ray Davis Jr. received the Nobel Prize in Physics in 2002. However, in detail, that data didn't agree with the expectation. The event rate observed in this experiment was only about 1/3 of the prediction. This problem was known as solar neutrino problem for many years. And this problem was actually confirmed by the subsequent experiments in the 80s and 90s. But unfortunately, in the 20th century, we are unable to understand what was the cause of the deficit. Then, this problem was understood very clearly by the snow experiment in Canada. This is the sketch of the experiment. So at the 2-kilometer extremely deep underground, they constructed 1,000 tons of heavy water detector. And in fact, there is a very good reason to use heavy water. If they use heavy water, they can observe the total neutrino flux, independent of the neutrino type. Also, independently, they can observe the electron neutrino flux. And by comparing these two measurements, Snow experiment was able to confirm that solar neutrino deficit was due to neutrino oscillations. Because, well, if they observe the total neutrino flux, independent of the neutrino type, the event rate was just as expected by the solar model. However, if they observe the electron neutrino flux only, the event rate was only about 1/3 of the expectation. And the sun can only generate electron neutrinos. Therefore, the discrepancy between the total neutrino flux measurement and the electron neutrino flux measurement indicate the existence of the mu neutrino plus tau neutrino flux on the Earth, but they cannot be generated in the sun. Therefore, neutrino must be oscillated. So this way, the solar neutrino problem was beautifully understood to be due to neutrino oscillations in 2001 to 2002. By the way, actually, well, people were convinced that the neutrino type was changed from electron neutrino to mu neutrino and tau neutrinos. But with this data only, very precisely speaking, there may be some other mechanism to change their neutrino type. Therefore, people wanted to have more direct evidence for electron neutrino oscillations. And for this, another experiment in Kamioka played a very important role. This experiment is called Kamran. And actually, this is 1 kiloton liquid scintillator detector. And this experiment observed neutrinos created by nuclear power stations. And in fact, there are many nuclear power stations at a distance of about 180 kilometers from this experiment. And if they observe these neutrinos, then they found this kind of lower flux than expected, almost expected, lower flux, almost expected. And this way, people were really convinced that electron neutrinos oscillate to other neutrinos, and therefore people are really convinced that solar neutrino problem was due to neutrino oscillations. Okay, so this was the discovery of the second neutrino oscillations. And since there are 3 types of neutrinos, there should be one more oscillation channel. And in fact, after the discovery of the solar neutrino oscillations, community's interest was the discovery of the third oscillation channel. And in fact, the third oscillation channel was discovered by these experiments around 2011 to 2012. I don't go into details, but these experiments clearly observed the third oscillation channel. And with these observations, the basic structure for 3-flavor neutrino oscillation has been understood. Okay, well, so far, I have explained the discovery of neutrino oscillations. But you may wonder why physicists were so excited with the discovery of neutrino oscillations or neutrino mass. Well, electrons have mass, quarks have mass. Therefore, in a sense, it's natural that neutrinos have mass. But still, we are excited with the neutrino mass. Let me explain why we are excited with the neutrino mass. Here, I show you the mass of charged leptons. There are 3 types of charged leptons, and the mass is shown by red colors. In addition, I show you the mass of quarks. There are 6 types of quarks. Therefore, these mass are shown by blue and green colors. Now, the discovery of neutrino oscillation was 20 years ago, and during this time, there were a lot of studies on neutrino mass. And now, we can reasonably tell you the absolute neutrino mass. And if I plot the neutrino mass on this graph, then the neutrino mass is here. So, first of all, well, neutrino mass is much smaller. And please be careful about the horizontal axis. Here, the 1 unit shows 100. So if the point is separated by 4 units, that means neutrino mass is smaller by 8 orders of magnitude. So if you check how much separation the neutrino mass compared with other mass, you notice that neutrino mass are approximately or more than 10 orders of magnitude smaller than the corresponding mass of quarks and charged leptons. 10 orders of magnitude or more smaller than the other particles' mass. So neutrino mass are extremely small. And because of this extreme smallness of the neutrino mass, physicists are excited. And we believe that this is the key to better understand elementary particles and the universe. Okay, now, because of this very unique feature, we still want to study neutrinos. Therefore, we want to talk about the future directions. By the way, in the previous page, I said that neutrinos, or the very small neutrino mass could be the key to understand the universe better. But why universe? Well, okay, let me explain. This is the photo of the far universe. You can see many stars and galaxies. And we know that these stars and galaxies are made of matter. We are made of matter. We know that there is no antimatter galaxy, no antimatter star. But this is a little bit strange. We know that our universe began with the Big Bang. And in the very hot Big Bang universe, always matter particles and antimatter particles are created simultaneously. And therefore, in the Big Bang very hot universe, the number of matter particles and number of antimatter particles should have been equal. But now, we can see only matter in the universe. What happened? Well, this problem is kind of understood. In the Big Bang very hot universe, the number of matter particles was, say, 1 billion. Number of antimatter particles was, on the other hand, 1 billion. Then, with the cooling down of the universe, if matter particle and antimatter particle meet, then they annihilate, disappear. So therefore, at present, we have only one matter particle that is coming from 1 billion one, this one. So we understand this happened. However, I said, in the Big Bang universe, there must have been equal number of matter particles and the antimatter particles. Of course, 1 billion one and 1 billion are almost equal, but not exactly equal. Therefore, we think we have to explain why there was an extra one in the Big Bang universe. And in fact, we do not know why there was this extra one. But we think that neutrinos with very small mass might be the key to understand this extra one, the big mystery of the matter in the universe. So, because of this big question, we'd like to understand neutrinos better. And in fact, in order to understand matter in the universe, we'd like to carry out the next generation neutrino oscillation experiment. And in these experiments, in fact, we'd like to observe if oscillations of neutrinos and those of antineutrinos are different. If they are different, this could be the first step to understand the matter in the universe. Therefore, there are two projects. One is going on, one is still planning. One is the DUNE project in the United States, and another one is the Hypercam project in Japan. And well, I want to show you a few more slides, but I don't want to go to too detail. Now, in order to study the matter in the universe, we want to study more on neutrino oscillations. However, the present Super-Kamiokande is not powerful enough, not big enough. Therefore, we'd like to have the next generation experiment. And in fact, this slide shows you that how Water-Cherenkov experiments were successful. Kamiokande IMB experiments observed neutrinos from supernova 1987A. They observed atomic neutrino deficit, and later this was confirmed to be due to neutrino oscillations. And this one, Kamiokande observed solar neutrinos, and Super-Kamiokande discovered atomic neutrino oscillations and also contributed to the solar neutrino oscillations. And in fact, Super-Kamiokande has been used for the far detector for the accelerator-based long baseline experiments. So these experiments really contributed a lot to neutrino physics and astrophysics. Therefore, we think it's natural to extend the Water-Cherenkov technology to the next generation. And well, this is a little bit more detail about the Hypercamiokande project. We'd like to construct a still bigger detector. It's going to have 74 meters in diameter and 60 meters in height. And the total and fiduciary volumes are 0.26 and 0.19 megatons, respectively. And this is going to be a very general detector. Therefore, we use this detector for studies of various neutrinos. neutrinos from the accelerator to study neutrino oscillations, study of atmospheric neutrinos, solar neutrinos. Furthermore, we'd like to observe supernova neutrino burst. And finally, we want to observe proton decays. That was the initial motivation of the Kamiokande experiment 40 years ago. And it's going to be really an international collaboration. At present, we have about 300 people from 15 countries. And in fact, the fraction of the Japanese in this project is only about 30%. So this is really going to be the international collaboration. But I think I skipped the details. Sorry, that was too detailed. So, but let me mention a little bit about the status of the Hypercam project. But well, again, I found this is a little bit too detailed. In short, I'd like to say the Hypercamiokande construction will begin next year, 1 year from now. And therefore, my message to you is, you are most welcome to work together in Hyper-K. This is really a serious message to you. We really want to work together in this project. Okay, so let me summarize. Atmospheric muon neutrino deficit was observed by proton decay experiments unexpectedly. Subsequently, essentially 10 years later, in 1998, Super-Kamiokande discovered neutrino oscillations, which shows that neutrinos have mass. The discovery of non-zero neutrino mass opened a window to study physics beyond the standard model of particle physics, and neutrinos with small mass might also be the key to understand the fundamental questions of the universe. And finally, well, I feel, well, actually, I was deeply involved in the discovery, and I feel that I was very fortunate. I had very good advisors, colleagues, and I was always involved in very good projects. And clearly, the neutrino physics will continue to be very interesting. Therefore, we really want to work together in the future neutrino project. That's all. Thank you very much for your attention.
Зараз почнемо першу частину запитань. Є дві людини з мікрофонами. Будь ласка, піднімайте руки, вони будуть до вас підходити по черзі. Задаємо запитання. Якщо ви не впевнені задавати питання англійською, ну, якщо що, ви попереджайте перед тим, щоб я встиг дати йому, сказати, що йому треба перекладати. Добре? Будь ласка.
Hello. Okay. Hello. Okay. So particle-antiparticle generating mechanism is different for baryons and leptons. Yes, for baryons it's produced due to CKM matrix, and for leptons it's produced maybe due to Pontecorvo matrix, maybe due to the fact that neutrino could be Majorana fermions. But these effects are independent. How is it explained that today universe has the same, like almost maybe equal numbers of baryon and leptons, that now universe is charge neutral? Like, is it explained now?
Oh, about charge neutral. Oh. Yeah, well, I'm sorry. I didn't think about that. I'm sorry. I don't have an answer to your question. I'm very sorry.
If I didn't misunderstand, at Kamiokande, the oscillations between electron neutrino and muon neutrino is negligible, yes? Oscillations are negligible.
Yeah, right.
But from the, like in the solar problem, the total number of electron neutrino equal 1/3. So in the solar problem, the oscillations, like, they are equal for every type. How can you explain it?
Oh, okay. Well, clearly, this is clearly explained within the framework of the Ponte-Colbo Maki-Nakagawa-Sakata matrix. I mean, well, the neutrino oscillations we discovered in Super-Kamiokande is between muon neutrino and tau neutrino, and the solar neutrino oscillation is from electron neutrino to muon plus tau neutrino, and the oscillation length is approximately 30 times different, and all these are understood within the simple three-flavor framework with the Maki-Nakagawa-Sakata-Ponte-Colbo mixing matrix. Length is one of the very important factors to explain this.
Well, first of all, thank you for the lecture very much. And I want to ask you, you've mentioned that there will be a huge contribution of the neutrino oscillations in the future for exploring the universe, right? But also, I've heard that there must be a significant interest from military structures, because neutrino oscillations can provide some opportunities to create means of communication, because they can cover tons of ground and pass through very different materials. So what is the current state of such researches, if you know it?
Well, thank you for this question. Well, certainly, in principle, we could use neutrinos for the way of communication. However, in my opinion, neutrinos are too inefficient to do this kind of communication, because you have to really create huge number of neutrinos to guarantee a detection in the far side. If you, well, I have never calculated, but in order to really create that kind of neutrinos, you need a huge instrument. And therefore, in my opinion, economically, neutrinos cannot be used for this kind of purpose.
Thank you for the lecture, and I know that nowadays we know a lot about three mixing angles and two difference mass in square, but what we know about the third one? But what we know about the third one, third difference mass?
Okay, well, let me confirm. So now we understand two neutrino mass difference. Then about your question is about the third one, third mass difference. Okay, so I think your question is related to the so-called sterile neutrinos. Well, we know, first of all, we know that there are only three so-called active neutrinos that can interact with matter. But physicists are thinking that maybe there are fourth neutrino, well, neutrino-like particles that do not interact with matter. Now, if this kind of particle exists, then we can define the third mass difference. However, in my opinion, the evidence for the sterile neutrinos, the third mass difference, is still weak. So it's too early to say anything about the third mass difference.
面白いレクチャーどうもありがとうございました。You mentioned that neutrinos might be responsible for the discrepancy, for the difference between matter and antimatter. Could you please a little tell us about how is that, how they can be responsible for this discrepancy? ありがとうございました。
Okay, thank you. Yeah, well, the whole story could be like this. First of all, neutrino mass is very, very small. And the present standard model of particle physics cannot explain this smallness. And typically, people introduce very heavy neutrino-like particle in order to explain the very small neutrino mass. And this very heavy neutrino-like particle should have existed in the very hot Big Bang universe. And the decay of this particle may contribute to the present-day matter-antimatter asymmetry of the universe. This is the whole scenario. But, of course, this is still an hypothesis. We'd like to know if there is really a mechanism to generate the matter-antimatter asymmetry in the decay of this heavy particle.
Firstly, thank you for a lecture. It was very interesting here. Well, I was wondering, how do neutrino detectors work?
Oh, okay, thank you. In fact, I'm sorry, I didn't explain how we detect neutrino interactions. Well, okay, let me explain. Neutrinos, of course, most of these neutrinos pass through the detector. Therefore, we have no way to observe them. But sometimes, one of these neutrinos interact with the nucleus in the detector, in our case, water. So if a neutrino interacts with the water nucleus, a charged particle is emitted. Then this charged particle propagates in the water. Then this particle emits Cherenkov photons. Therefore, we can observe these photons by the photodetectors in the detector. This way, we observe these neutrinos. Okay?
Hello. Thank you very much for lecture. It was very interesting. And I have one question. Now we have in all experiments, such as colliders, we detected only neutrons with left chirality. Maybe mass oscillation can somewhat explain why we do not detect neutrons with right chirality.
I'm sorry. Could you say again? I'm sorry.
We detect neutrons only with left chirality. Yes. And why we do not detect neutrons with right chirality? Neutrinos, I mean, sorry.
Is it working? Okay, now I understand part of your question. Could you say again?
With neutrinos with left chirality, yes? We detect chirality, you understand?
Yeah.
Why we do not detect neutrinos with right chirality in experiments?
I see. The question is, we only detect left-handed neutrinos. We have no evidence for right-handed neutrinos. I think that is correct. And the question is why we cannot detect right-handed neutrinos. Okay. This is a very, very high-level question, I'm afraid. I don't have any good answer to this question. Well, maybe, well, if I answer without seriously thinking, maybe I will tell you something wrong. Therefore, I want to think more seriously about your question. I'm very sorry.
So does thanks for lecture, first of all, and does the antineutrino oscillate differently from regular neutrinos? We can, there is, in standard model Lagrangian, there is a charge current part, and simply PNMS matrix just commutes with other gamma matrices and others, so we should expect that they should oscillate the way that a regular neutrino does. So, and you said that we should look at, so why does the antineutrino should oscillate differently from neutrinos?
Oh, okay, thank you for this question. Why antineutrinos could oscillate differently as neutrinos? Well, in the PMN, Maki-Nakagawa-Sakata-Ponte-Colville matrix, there is actually a phase. In addition to the three mixing angles, there is one phase that is related to the CP violation, matter-antimatter difference. And because of the existence of this phase, there is a possibility that neutrino oscillations and anti-neutrino oscillations could be different in some detail.
Thank you for the lecture. I have the question. Nowadays, we know that our universe moves and accelerates in all directions, yeah? And we know about this acceleration. But further, we didn't know about that neutrinos have mass. So my question is, does the knowledge that neutrino actually has mass can impact on the backwards acceleration of the universe? So, thank you.
Yeah, thank you very much for this question. In fact, yes, neutrinos have very small mass. Therefore, in principle, neutrinos affect the expansion rate. However, neutrino mass is too small. Therefore, neutrino mass itself cannot significantly slow down the acceleration. In fact, the effect of the dark energy is much bigger. Therefore, the acceleration is, expansion is accelerating.
Культ соціології та психології. Загалом питання не зовсім фахове, але особисте, вибачте. Для Альберта Ейнштейна було в 6 років, змінило світогляд така невеличка подія, як подарунок компаса батьком йому. І він дуже надихнувся цим компасом. Загалом це стало його натхненням, конструктивним натхненням до занурення в фундаментальну науку. Що для вас було конструктивним натхненням, що дало шлях зануритись в фундаментальну науку? Вибачте. Дякую.
Okay. Thank you very much for this question. Well, actually, it's difficult to say. Well, okay. I don't have any particular event, but when I was a high school student, in order to decide what I'm going to learn in university, undergraduate course, simply because of the interest in physics, I decided to select physics. Then in the undergraduate course, I learned that the physics is actually much more interesting than we learned in high school. So I decided to continue, and in the graduate course, I began the Kamiokande experiment. And actually, to be honest, I want to say that I'm not the person who likes to study papers, reading papers, and so on. But the work in the Kamiokande experiment was really interesting. So when I was the PhD course, I decided that I want to be a physicist. So my decision was always step by step.
Thank you for the lecture. I would like to ask if you can, I would like to ask about this plot where you presented your results from Super-Kamiokande. There was labels for electron neutrino, there was FC, and for mu neutrino, there was FC plus PC. What does this stand for?
Are you talking about?
This old slide. Yeah. What is FC and FC plus PC?
Okay, well, sorry. This is for experts. FC means fully contained events. Okay, that means neutrino interactions occurred inside the Super-Kamiokande tank, and all the charged particles stopped inside the tank. That is the fully contained event. And PC means partially contained events. That means neutrino interaction occurred inside the tank, and at least one particle exited from the detector. That is the partially contained event.
Thank you very much.
Yeah, thank you for the lecture again. And my question is, so if there is an antimatter which is caused by negative particles, with negatively charged particles, so, and can we assume that these neutrino have negative mass? So basically, I've heard about this theory, and you maybe heard as well, but I'm not sure whether it's proved or not. And can you explain how can we put this in our minds that there is a...
Yeah. Thank you. Well, okay. Well, let me explain with the protons. Protons have positive charge, and the antimatter particle is antiproton. It has negative charge. Okay, but the mass are exactly the same. Both are positive mass. So the same should be happening for neutrinos.
You don't believe in the negative mass?
No.
You see, when we say about oscillation, as in the classical physics, we take into account two moments. It's mass and restoring force. Your oscillation is eigen oscillation and Fawcett oscillation. Eigen frequency of your oscillation, it's very important parameters. It's, to understand this phenomena, it's very important to understand the restoring forces of, in this process.
I see, yeah. Well, certainly the eigenfrequency for the oscillation is very important. This is directly related to the neutrino mass difference. So that way, it's very important. But about this force, actually, I'm not sure if I can connect to the neutrino physics.
День. Вы упоминали о том, что вы использовали ядерный реактор для того, чтобы изучать нейтрино. Но ведь в Земле тоже есть радиоактивные элементы, которые излучают нейтрино. Пробовал ли кто-то, используя нейтрино, обнаружить эти радиоактивные элементы?
Oh, okay. Well, thank you very much for this question. Yes, the Earth contains radioactivities. Therefore, Earth is yes, neutrino emitter. And in fact, already there are at least 2 experiments that detected neutrinos from the Earth. And well, actually, the detection of these neutrinos are extremely difficult because of the low flux. But very pure liquid scintillator experiments observed neutrinos produced by the Earth. And with these studies, people begin to understand the interior of the Earth.
Thank you very much. Could you comment, what is your opinion about possibility to investigate neutrino mass hierarchy with long-base experiments?
Neutrino mass hierarchy?
Yes.
Okay, yes. Well, certainly this should be decided by, well, determined by experiment. And at this moment, the Super-Kamiokande atmospheric neutrino studies suggest that nu3 is the heaviest state, and also that T2K experiment, that T2K is a long baseline neutrino oscillation experiment generating neutrinos at the JPAC and detecting neutrinos at Super-Kamiokande. This experiment also suggests that nu3 is the heaviest. But unfortunately, the experimental significance is only about, say, 2 sigma level. Therefore, we need the next generation experiment to really know the neutrino mass ordering.
Good morning, and thank you for the, I'm here. Thank you for the lecture again. I have a question. You said that the nature of neutrino is changed due to their oscillations, and that they are interacting with some kind of as every kind of matter. So I wonder, is there any physical measure, not measure, but is there any chance, or at least physical theory, which could be used to stop neutrinos from oscillation, to catch them in some kind of state and make them possible to observe in that calm state?
Okay, thank you. In fact, yeah, well, change their oscillation. Well, okay, let's think about the solar neutrinos. At the center of the sun, when solar neutrinos are generated, they are electron neutrinos. And actually, when we say electron neutrinos, this actually contains 3 mass states, nu1, nu2, nu3. But for the moment, maybe we forget about this small component of nu3. The very important physics with solar neutrino oscillation is oscillation itself is changed by the existence of the matter, solar matter. And in fact, because of this effect of the solar matter, when they exit from the surface of the sun, these neutrinos are essentially the nu2 mass state. Therefore, after that, they should not be oscillating. So that way, I think this is the only example that can change the oscillation pattern.
Hello? Okay, like a mathematician question here.
Oh, yeah.
Hello, yes. Like in the standard model, neutrinos are described by Weyl spinors, left hierl. But we understood that they have mass. But mass particles, they have both left hierl and right hierl components. Where appears this new degree of freedom? How it appears?
Oh, I'm an experimental particle physicist. I'm not a good person to answer to this question. I'm sorry.
Dear Professor Kadzita, thank you very much for nice lecture. My question is related to relic neutrinos, cosmic neutrino background, analogous to CMB. Some future experiments promise us the possible future detection, but we know that, of course, relic neutrinos have very high number density, but very, very low energies now. Therefore, their cross-section, the interaction cross-section is very low, very small. Is it possible to detect them now, in nearest future, for example, in nearest 10 or 12, 20 years?
Yeah, okay, thank you for this question about the cosmic neutrino background. Well, I think, as far as I know, there's no one who has the idea, realistic idea, to observe these very cosmic neutrinos. So if you ask us if we could have any chance to observe these neutrinos within 20 years, I would say it will be very difficult.
Yeah. My question is, you mentioned proton decay, the first goal of the Kamiokande, and the prediction was not confirmed, theoretical prediction. But you mentioned that you look forward for detecting proton decay. What is new predictions? What is the limit? What is the order of half-life?
Okay, thank you. Yes. Well, in the 70s, the proton life prediction was about 10 to 30 years. I think nowadays there's no particular value for the prediction of the proton lifetime, but some of the theories predict that proton lifetime should be around 10 to 35 years. So, and in fact, in the next generation experiment, if the real proton lifetime is 10 to 35 years, this experiment can detect. So, yeah, we really want to observe. But, of course, this is not guaranteed.
Hello, thank you for the lecture. And my question is, you told us that Kamiokande and Super-Kamiokande experiment was about 15 years ago, and in your observation about oscillation of neutrinos and their mass. So my question, why did you get Nobel Prize in 2015?
Why I get the prize in 2015?
Not 20 years.
I have no idea.
My question is about the proton decay. So how you will recognize that this is the proton decay, and what result will show that it is fixed?
Yeah, thank you. In fact, from now on, the search for proton decays are going to be more and more difficult because of the more and more background from neutrino interactions. And therefore, basically, we are going to use the decay of the proton from hydrogen of course, there are protons inside the oxygen. However, these protons are moving inside the oxygen, so-called Fermi motion. And in fact, because of this motion, the final state has the finite motion, and therefore, that means finite momentum. Therefore, this is rather difficult to separate the proton decay signal and the neutrino interactions. However, if the proton decays from the hydrogen atom, then initially this hydrogen should be stopping. Therefore, the final state of the proton decay should have a perfect momentum balance. This is really a very important feature for the future proton decay search. And this way, we'd like to observe the real proton decay signal.
Good morning. I wanted to ask you about what are the predictions about massive usage of neutrinos in the future?
Massive what?
Massive usage.
Massive usage?
Yes.
Of neutrinos?
Yes.
Okay, thank you very much for this question. Well, of course, first of all, I think neutrinos will not be useful for improving our daily life. However, neutrinos could be useful for other fields of science. For example, people would like to understand the interior of the Earth, and for this, neutrinos could be useful. That way, we may contribute to the, neutrinos may contribute to the other science field.
Yes, another question about the experiment, Super-Kamiokande. So we have this cylinder and photodetectors at the walls of the cylinder. What are the benefits of this setup against the other neutrino observatories like IceCube or Baikal?
Aha, I see. Oh, well, okay, well, in case of IceCube, they have the even larger volume. They have the 1 cubic kilometers, and they need to have the strings of the photomultiplier tubes because the transparency of the light in the ice is limited. Therefore, they need to well, it's not possible for them to have the similar shape as Super-Kamiokande because the volume is too big. Therefore, even if something happened at the center of the detector, the photon may not be reached to the wall or surface. Therefore, they need to have many strings inside the volume. But in case of Super-Kamiokande, Super-Kamiokande is much smaller than IceCube. And therefore, if we have the photomultiplier tubes at the surface, essentially most of the photons arrive at the surface.
So hello, and my question is, have ever you or your colleagues or people you work with thought about putting a huge convergent lens in space and gather all neutrino in one point with high concentration and study properties of them there? Once again? Okay. So my question is, have you or your colleagues or people you work with thought of putting a huge convergent lens in space and gather all neutrinos in one point and study their properties there? So once again, as you mentioned, different space objects like sun, for example, they radiate neutrinos. So I asked you if you or your colleagues or anyone you work with thought of putting a huge lens in space and gather all these neutrinos in one point with detector and study their properties in this point.
Putting some object on the space and study neutrinos.
Lens, which gather neutrinos in one point with high concentration of them.
Well, okay. In our understanding, the kind of lensing effect is not expected for neutrinos.
Ah, okay, I understand.
Yeah.
Можна, будь ласка, переклад? Вітаю, дуже дякую за лекцію, вона була дуже цікавою. Моє питання буде таке. Чи думали ви в дитинстві, в студентські роки, чи будете ви займатися наукою? Чому обрали саме фізику і як до цього ви дійшли? Чому вибрали саме фізику, а не якусь іншу із наук? Дякую.
Well, okay, thank you very much. Why did I choose physics? In fact, that was not trivial. Well, when I was a high school student, in order to decide what I'm going to learn in universities, actually, physics was one of the choices, but I also thought about other choices, such as biology, or actually, that was more than 40 years ago, but I was quite interested in the environment of the globe. So I may have selected some other field, but somehow I decided physics.
So, hello. In your presentation, you had written that you are very happy to work with such great colleagues, with such great projects. Is it started from the beginning of your career or only after 10, 20 years of your work? Thank you.
Well, actually, I think, first of all, I was really lucky that I was involved in Kamiokande when I was the graduate course student. And since then, I was always very happy to work with my colleagues.
Last one question.
One of the main questions in physics today is the question about the average density of our universe. And my question is, if the neutrinos' mass have any effect on the mass of the whole universe, and can we make some statements about its future?
Okay, thank you. Yes, well, of course, neutrinos have mass. Therefore, neutrinos can contribute to the total mass of the universe. However, the mass of the neutrinos are too small. Therefore, the neutrino contribution to the total mass is really a small fraction.
Давайте подякуємо професору за лекцію, за питання.
Thank you very much.